Okay, let's go ahead and get started. Thank you for joining us today for day one of a two-day HPRC short course entitled Introduction to Finite Element Analysis with ANSYS. It is my pleasure to introduce the instructor for today's short course, Dr. Umair bin Asim. Dr. Asim is a postdoctoral research associate in the Microstructural Mechanics for Materials Design group here at Texas A&M University. If you have any questions during the presentation today, please post them in chat or raise your hand. Again, let me welcome everyone, and with that, I will pass it over to Dr. Asim.
Everyone. Hi. Can all of you hear me? All right. I need to check. I cannot see my video. All right. You can see my video as well. Cool. As Liza very kindly introduced me, my name is Umair. I'm currently working with Dr. Ankit Srivastava and in CREDS. The idea for today's session is to introduce those of you who are joining us under OREU, and some of the colleagues from the MSc department has showed interest in having an introduction about the FEA as well. So we'll be catering for both of these two kinds of audiences. I understand that some of you has already installed ANSYS on your personal computers. So if you go ahead and use it on your personal computers, it's perfectly fine. But those of you who don't have it, we'll be using the HPRC for running the ANSYS. So some things which I want to introduce from the very beginning, that if you look at your Zoom's panel on the bottom, there is a icon which is titled Participants. So if you haven't already, please click on that so that there is a panel which will open on the right hand side of your Zoom window, which has a couple of options there. There are certain icons which shows yes, no, go slower, go faster, and some more of them, some more options there as well. The chat is there on that panel as well. If it is not already there, then you need to click on the chat icon as well to open the chat window. During the session, let me share the screen. During the session, you can ask questions. You can stop me wherever you want me, wherever you're stuck, by raising hands. I'll try to keep a check on the participants panel as well, to keep an eye out for anybody who has any problems. And Lisa, can you please tell me if there is any concerns on the chat, because apparently because of some reason my participants panel has gone now while I'm sharing the screen. All right, thank you. So I'll tell you how you can share your screen to get some help if you need, or if you're stuck somewhere at a certain step. I'll let you know how to share your screen so that I can help you individually as well. So without any further delay, let's start. So this is my contact information. Even after this session and the next session we'll have, if you have any questions, you can of course contact me if you have any questions. All right, so this is going to be our agenda for the day, for this session. I'll start with one of a very simple problem, but a problem which certainly need an FEA analysis. Then we will, I'll take you through each of the major steps involving any FEA analysis, which is pre-analysis and startup. We will be going through how to create a geometry, a simple geometry, and I assume that most of you has some CAD knowledge before coming to this session, but even if you don't have any, I'll take it at a very slow pace. Then I'll take you through a step called meshing or discretization, which is a very important step in any FEA analysis. Then the physics of the physics will be set up for the model which we have generated. Then we'll solve our problem and analyze the results. Then we'll go through the verification and the validation of the results which we got. And at the end, I'll discuss some exercises with you for your own practices. So the problem which we'll be solving through FEA today is going to be a solid plate with a hole in between, the circular hole in between. So the dimensions of the plates are going to be length times width, which values are 5 by 10 inches. We will be loading our plate by a distributed load of 1/10⁶ psi on the right hand side, whereas the left and the bottom side will be constrained for zero displacement. In addition to that, the thickness of the plate is very small, which is roughly 0.2 inches. And the Young's modulus is 29×10⁶ psi for the material which we are, the material with which the plate is made. So before going into the details of this particular problem, or like before starting to solve this problem, I need to point out some of the things here. I should have a slide about applications of FEA before this one, or the motivation of doing FEA, but unfortunately I forgot to add that slide here. I'm sure I'll be sharing that information in your next session, before the next section. But the motivation of solving I'll highlight what are the motivation of solving this problem using FEA. So since most of us are coming from a background where we have already taken a solid mechanics course, we know that if we don't have a hole in the center of this plate, this problem is a very simple problem which you can solve probably within a minute or two, just by using very simple analytical formulation. But the addition of a circular hole in the middle of the plate is introducing a kind of nonlinearity in the geometry, because of which any available analytical formulation cannot be directly used here. Although there are certain analytical relations which are already present for a case of a hole in a plate, but then again, those solution and the results are for a case where the plate has infinite dimensions. We very well know that although those relationships can be approximated for finite dimension of the plates as well, but it will not be an exact solution. So one of the motivation of using FEA is in those cases where we have non-linearities in the geometry and the elementary analytical solutions cannot be directly used to solve for the useful information. So as I already mentioned, that this hole in the center is going to be the non-linearity for which we'll be solving this problem for. So this is what I said, that analytical solution exists only for the infinite plate with a hole. So just give me a second, because I cannot see the chat window, so I'm not comfortable whether there is any questions. So this is the participants window, and here is the chat. All right, this is the chat. All right. So I'll take you through some of the basic pre-analysis information. The main reason of doing pre-analysis in any of the FEA solution is to have some rough idea about what kind of results we are going to be, or what kind of results are expected out of this analysis. So this is kind of sanity check, and it is required to see whether we are not doing any kind of very major mistake while setting up our problem or setting up our physics. So pre-analysis setup is almost always very necessary in any FE analysis, or for that case, any simulation, so that you need to back your results with some kind of analytical relationships to establish the sanity. So this is some of the mathematics. I don't expect you to understand each and everything of them. I have shared it here just for the sake of comparison and to make some kind of go-to place to check whether the results are within the limit or not. So some of the results which are mentioned here, under the case of the loading condition, which I've already mentioned here, that we are loading this plate of this dimension with this much load, how much displacement we expect out of this particular applied load, like how much deformation is going to be there in the plate. And specifically, we are going to be interested in the change in length of the plate. So how much length has been increased due to the load application of the load. Then one more thing which we'll be interested in going to be radial stress. So this is the stress component, which is going to be the value of R is going to be the center, and as we go away from the center, so this is going to be the. Can you see the mouse pointer? Great. So the R direction is going to be that component, and in that direction, the value of the normal stress, we'll call it radial stress. And this is the relationship for the radial stress. Keep in mind that all of these relations are for the case where we have an infinite plate and a hole at the center. So the value of sigma naught is the nominal stress way away from the hole. So which is the applied stress on this plate. The value of sigma naught is that. A is the diameter of the hole. And R is the radial location away from the center. So the value of R is going to be 0 at the center of this hole. And as we go away from hole, that is going to be the dimension R. And theta is going to be, so I haven't drawn the axes here, but imagine the axes to be like, the value of theta is 0 along the positive x-axis. And as we go counterclockwise, the value of theta increases from 0. And it goes all the way to 360 degrees. So if we want to, or we are interested in finding out the value of sigma R in any remote location within the plate, we just have to know the value of R and theta, and of course the applied sigma naught and the diameter of the hole to get an approximate value or an estimated value of sigma R. For a case, again, I'll keep on emphasizing on that it is for an infinite plate. So even if we apply in this case, the result is not going to be exact. Then there is another component of the normal stress, which is the tangential component. So tangential component is going to be like this in the theta direction. And again, the values which we need to know, the value of tangential stress in any of this location is the value of sigma naught R, A, and theta. Similarly, there will be a shear stress component as well in the R theta direction, and this is the relation for that. Going back to the displacement, I skipped this part. So this is the analytical solution for a case where we have the plate of exactly the same dimensions, except there is no hole in the middle. So if you assume that there is no hole in the middle, we can use this very simple, as I told you, that for those kind of cases, you can very easily use the very simple solid mechanics sort of relationship to get the value of the displacement or the deformation in the plate. So sigma xx is going to be the amount of distributed load we are applying on the right hand side, and times the total length, and divided by the Young's modulus can give us the amount of deformation the plate will undergo in a case where we don't have a hole. So that is, if you calculate it, it's going to come out to be 0.34 inches. I'll come back to it once we have already gone through the FEA and we have the results, so that we compare these two side by side. Then we will be interested in the normal stress component in the x direction as well, and the relationship for that is where it is, yeah, at the back, at the bottom. So this is the nominal stress in the case where this is sigma naught is the applied load on the right hand side, the distributed load. Then if we want to calculate the nominal stress is going to be the value of stress at this location here, assuming that we don't have a hole here, but we just assuming that this is the total cross-section area. So for this cross-section area, the value of nominal stress is coming out to be 1.11. But since it is not just an area, rather a hole in the middle, so it is going to create a concentration of stress around this particular hole. So this relation again can be used to approximate the value of the stresses, or the maximum value of normal stress in the x direction around a particular circular hole. So for a circular hole in an infinite plate, the concentration factor K is 3. And if we multiply that factor by the applied load, we get the maximum value of sigma xx, which we may encounter in a case where we have a hole in an infinite plate. So these things may not be making a lot of sense right now, but once we have the results for this particular analysis, we'll come back to it and compare these two things side by side to get a better idea. All right, so without further ado, let's start the ANSYS and start doing some FEA. So in order to do that, you must have an HPRC account and you must be running a VPN service. So most of my colleagues from MSCN has already known how to use the VPN, and they may already have ANSYS on it with them. The guys who are joining us from OREU may already have attended Dr. Demkovich's session yesterday, so they already know how to log into HPRC and what the VPN service is. But if somebody is joining us for the first time, this is the website which we'll go to. So let's go there. So all right, so that net address is in the chat as well. So it is portal.hprc.tamu.edu. So once you are here, click on ADA on-demand portal. You'll be using ADA. So if you haven't already logged in, you'll be asked to enter your net ID and the password to come to this window. Once we are here, I'll click on my interactive sessions here. It will open a new window. All right, so you don't have permission to access. Does that mean I need to request the account? Are you logged into VPN? So do you have this VPN here, and are you connected to VPN? All right. So if you are already connected to, this is who, Jessica. Jessica, do you have ANSYS already installed on your computer? I assume that you already have it. If you already have it on your personal computer, use it from there. It's fine. All right, you can use it remotely then. use it from there. It's perfectly fine. All right. So rest of us who have reached on to this window, let's click on ANSYS Workbench. This is the environment which we'll be using. So make sure that you have ANSYS 2019 R3 already selected in the ANSYS version. Number of hours is 4, although the session is not going to run for that long, but just for your sake of your practice and stuff, keep it 4 for now. You can always come back if you need more time, but keep in mind that this session is gonna end after 4 hours. So keep on saving your progress. Okay. Number of course, 1 is more than enough for this simple problem which we'll be solving. 2 GB memory is fine. Node type GPU. This is the default, and this is the only option you have. If you want, you can get the information about whether your session is up and running via email. So you need to check this box and enter your email, but both of these things are optional. So once you have selected all these things, ANSYS 2019, 4 hours, number of cores 1, and memory of 2 GB, go ahead and click on launch. So this thing will appear. So this is the session which is created for you. It says that, all right, so you may have to wait for a couple of seconds for it to be ready for using. Before going into this, let me go back to my slides and check whether there is something more we need to take care of. So we have selected data, net ID and password we have used. We have selected all these things. We have clicked on the launch. All right, so yeah, one more thing. So keep this window open, and you can see on the top in the toolbar, there is an option for files. There are 2 options there. One is home directory and one is Scratch directory. So if you click on any of these 2, this is the kind of file explorer which is going to be open for you. This platform you can use to share the files between HPRC and your own personal computer. So we will be saving all our progress on our Scratch directory. So the Scratch directory, for that we need to go to, all right, let's go back. Files, Scratch. So this is the Scratch directory. So you will be saving all your files here, and once you have saved them and you are getting done with your session, make sure to download the files to your personal computer, because none of this data is backed up. So if like it will be removed after some time. So make sure for your own future reference, keep download the files once you are done with your task for today.
I'm sorry to interrupt you. I just wanted to correct that. We do not remove files in Scratch. They're just not backed up.
They are not backed up. All right, cool.
Okay.
Cool. So we can use it for future references as well.
Yes.
All right, perfect. Thank you. Thank you, Lisa. All right, so yeah, you can keep the files here and you can download it if you have. All right, one more thing to add here. This is one of the way of using ANSYS for all the students who are here. There's another way of using ANSYS, of course. Let me see whether we will be able to find it or not. So you can install ANSYS on your personal computers as well for the current students only. And to get this software for your personal computer, you need to go to this address, software.tamo.edu. You need to log into it. Unfortunately, it won't be showing anything for me, but just keep a note of this particular address. You need to log in. Once you are logged in with your net ID and password, all the available softwares will be shown here. and among the list, you will find ANSYS there as well. So this is the student version of the ANSYS, which is free for the TAMO students. So you can download it from there for your own personal computers as well. All right, so let's go back to the, all right. So this is where I assume all of you already are. Has anyone have any problem getting to this point? All right, I assume that everybody's here. Just wait a second, I'm just reading the chat. All right, so let's click on the launch no VNC new tab. All right, I was telling you about sharing your personal screens if you are stuck with at any step, so that I can help you. So this is the button which you will be using to share your screen with me. So if you click here, oh, in order to get the link, you first have to have the session started. Let me start the session first. Cool. And then view a shareable link. Where it is. Oh, there's something wrong. All right, since this is my own computer, that's why it is doing it. Lisa, it is not giving me a shareable link.
I actually do not know why it would not get you. Oh no, you have to just right click on it. Right click and then copy link. There you go.
Copy link. All right, cool. So if you need to share your screen with me, just right click on that, copy the, so what I did, I right click on this, copy the link address and paste it in the personal chat. So make sure that it is directly personal to me, so that I'll help you wherever you are stuck. So, okay, let's go and start with the ANSYS. So I clicked on launch no VNC new tab, and this is the tab which opened here. So this is the environment for the workbench. Let me make sure that your Zoom settings are fine, and click on maximize at the start, so that you can see the status bar, this toolbox, and the complete toolbar, because there are going to be some messages which will be on this bottom right, bottom left corner, to keep track of the things. So make sure that you can see all of this. So if your window is not already maximized, click on the maximize button in the corner, right corner at the top. All right, so whenever you get an interactive session for the ANSYS workbench, this is the environment which will open in front of you. Make sure that you don't close this window. If you ever close this window, all your unsaved progress will be lost. So make sure that you don't close this workbench window unless and until you want to end your session, right? So I can't emphasize enough on this particular point, that don't close this window. I guess I have put it in red in the course notes. There it is. Yeah, make sure not to close the tab and keep on saving the progress, right? If you, sorry, not the tab, the individual window. If you accidentally, where it is, yeah, if you have accidentally closed this tab, you can open it again by clicking on launch no VNC new tab. But if you close this window by pressing this close button at the corner top, the session will be ended, and all the unsaved progress will be lost as well. So make sure that you keep on saving your progress while you are moving ahead. All right, so if I go back, quickly go back to the, wait, to this problem. So this, we are not dealing with any kind of velocities or accelerations and stuff like that. And the rate of application of load, we are not bothered about that either. So this particular problem is a quasi-static problem. Although there's going to be some displacements happening there, but we are assuming that they are going to be happening at such a slow speeds that we don't it don't have any kind of dynamic responses added to it. All right. So what we'll be doing, let's go back to workbench. So there are all the kind of possible kind of analyses you can do using the ANSYS. Although there are a lot of them related to the CFD or computational fluid dynamics, there are certain problems which are FEA problems, but related to other physics things. But what we are interested in is a structural problem, and that structural problem is a since it is a quasi-static structural problem, so we will be using this thing in the toolbox. So before going ahead, what we'll do, we'll just click on static structural and drag, wait a second, it's not, and drag and drop it to the project schematic. All right, it is not taking my clicks. All right, there is something wrong. Let me close it. All right, let's see. Yeah, all right. So if it seems like that things have frozen up, you can close the tab. Again, never close this thing, close the tab and relaunch your NoVNC window. All right, so what I'm gonna do in order to, since we have already established that we are going to be doing a static structural analysis, so just click on this and drag and drop it to your project schematic. So as soon as you click, a small green box will appear here. So just drag this thing to that box and let go of the mouse button. So it will add a static structural problem here. You can name it anything. For now, I'm just leaving it as is. So this is how any ANSYS FEA problem can be solved or like initiated. So you'll come to the workbench and drag and drop a static structural, or in a case where you have dynamic effects as well. So you'll be using a transient structural and drag and drop it here. You can see that all the major steps which I have already mentioned in the, all right, I'm not gonna go back and forth. I guess that most of you can already see it this way. I'm not going into the slideshow. All right, so you can see that these are the steps which we have. So geometry, mesh, physics setup, solution, and results. So you can see all these steps here as well. So you have, they may not have the same names, but the steps are roughly the same. So there is a geometry here, then you have model, then you have setup, then some solution, and then results. So these are the steps which are involved in any of the FEA analysis you will be doing, be it on this software, which is ANSYS. If you go back to the interaction session, you can see that there is one more software called Abacus. So this is another FEA software which a lot of people use. So it has roughly the same steps as well. Then I don't know whether you're aware of it or not, but most of the people use SolidWorks these days as well for simple FEA analysis. So all of these FEA softwares roughly has the same basic steps involved. The principles which we learned today are applicable to all of these things, although the environment and interface are going to be different for all of them. How the things work or how to do a thing in each of these may vary from one to another, but the major steps remain the same for all of them. So let's go back and see what we need to do next. All right, so we have already familiarized ourselves with, let me go back to, see, I cannot see the status bar right now. So that's why I'm saying that we need to click on the maximize to make sure that we get to see this status bar. So this is the status bar. If there's what the workbench is currently doing is going to be shown here in the status bar at the bottom left corner. On the, if you have any errors and the workbench is communicating with you by telling you that you are doing something wrong, it is going to be shown here in the messages. If it is undergoing some kind of analysis, that progress will be shown here in this tab, and certain other options. But I am most interested in this status bar at the leftmost corner. This is the toolbox which I've already introduced you. This is going to be the toolbar. There are ribbon bars. These are called ribbon bars. It will be appearing in the consequent other environments as well. So if I say ribbon bar, so it means that the region under the toolbar area. So that's taken care of. What's next? All right, my options under analysis systems are different. I don't see static structural option. All right. So what are you seeing under the analysis system? Again, this is, I guess, Jaskirat, it's not about version, it's about the license. If you don't have the right licenses, you won't see all of these things. So are you sure that you are logged in through VPN? Because if you are not logged in through VPN, you won't be seeing all these options. Yes, yes. So this is the problem. This is the problem. So if you don't have the licenses, it won't be showing you all these options. So you said that you don't have an HPRC account. All right. Yes, this is what I was about to mention it to you, that since the whole, again, I forgot to mention it, but you have already accepted it when you were logging into the session, that this whole session will be recorded. So if you don't want to be recorded, you can mute yourself and turn off your camera. And even if that is not enough, you can log off, and this whole session will be recorded and will be shared later on. So since the disclaimer was already there when you were getting into this session, and I forgot to mention it in the beginning. All right, so let's move on. Beside Jaskirat, is there anyone else who has trouble getting up to this point? All right, there's none. So let's start. Let's go back to the slide. Let's end this slideshow so that I don't have to worry about switching between the two windows. All right, so we have already selected the static structure. You must have seen, you may have noticed that the units here are the US engineering units. Yeah, yeah. So, so you can see that you have US units here. So first thing which we will do, because the workbench assumes that the SI system is the default system. So if you are using anything other than the SI system, you need to first establish which units you will be using. And I cannot emphasize enough on this point that the most of the times the problem with most of us while doing FEA is the inconsistent units. So make sure everything you enter for the properties and for the geometry dimensions, you use consistent units. Otherwise, there's a very well-known thing about FEA that it is a black box. And if you put bogus data in, you'll get bogus data out. So it don't have a brain of its own. So you need to take care of that side. All right, so first thing, we'll change the units to the US engineering units. So for doing that, and you will need to do it a couple of times while you will be entering the data in the workbench. So if you click on the units in the top in the toolbar, you have the options of SI, metric system. All right. So the default was not SI, it was metric. And you have US customary and you have US engineering. So for this analysis, we'll be using US engineering units. So click on that, and just to make sure that the tick mark has shifted to this. So once you have done that, we need to create a new material which has this kind of properties. Let me add one more thing, the Poisson's ratio is 0.3. All right, so we need to create a new material which has these properties, that it has the Young modulus of 2.9 10 to the power 6 psi. Is it consistent? Is it 29 or 2.9? 29. My bad. It has 29 10 to the power 6 psi Young's modulus, and the Poisson's ratio is 0.3. So let's go back to the workbench and create that material. So in the engineering data, double click on that. So there's going to be a new tab which will open called engineering data. At the top you can see right now there are certain filters installed here, which is this filter is selected, filter engineering data. So you can see in the toolbox, now the toolbox has changed. When you were in the project window, the toolbox was showing you the kind of analysis you can do. But once you are in this environment of the engineering data, this toolbox is showing you the kind of engineering data you can assign to a particular material. All right. So I'm not going to go through all of them and explain what which option does what, but some of the most important are the ones are, for example, in the case of physical properties, you have density, some thermal expansion, some coefficient of thermal expansion, melting temperature and stuff like that related to the physics or the physical properties of any material. Then the mechanical behavior in the elastic region. So it can model or you can model a linear elastic material, you can model a hyperelastic material, you can have plasticity in your material as well. Creep behavior is there as well. Some fatigue analysis you can do. Strength analysis, if you are modeling gaskets and stuff, those kind of models are already there as well. If you're modeling viscoelasticity, damage, cohesive zones, fracture criteria. So these are some of the mechanical behaviors which are already built into this environment, and you can just use those models directly and just enter the parameters for the material you are using, and you can simulate those material behaviors as well. So for today's analysis, we are doing a very simple and the basic one. So we are assuming that we will not exceed while during these conditions, during this problem conditions, we will not exceed the elastic limit of the material. So we'll stay within the elastic limit of this particular fictitious material which we have created having these properties. So we don't need to bother about all these things for now. The most important things which we will be interested in is going to be the linear elastic part, and we will be assuming that our material is an isotropic have isotropic elasticity, so we don't need to worry about the other options either. But if some of you are modeling some of the composites and the sort, for example, wood or CFRPs and stuff, You may need to use the orthotropic elasticity. If you are doing something on the grain level, you know that the metallic grains and even the ceramic grains don't have isotropic elasticities, rather they have anisotropic in it. So you may want to use the anisotropic elasticity for those kind of cases as well. But for today's problem, my plate is made out of a material which has isotropic elasticity. So just to introduce, so right now there is a default material already entered there, which is called structural steel. This is not the material which we will be working with, since we already are provided with some kind of material property. So we will establish a new material. So if you want to start or enter a new material, just click here, name it anything. I'm going to call it agenium. And now you can see that all these things you can add. If you extend, you can just click on that and it will be added here. So I am right now only interested in its isotropic elastic behavior. So I'm just going to click on it, and it will add this material behavior, and you can see it here. All right. So this yellow boxes are telling you that these are the minimum amount of data that you need to enter for it to work for isotropic elasticity. All right. So the two things which we have to provide are the Young's modulus and the Poisson's ratio. So the Young's modulus, which is given to us, is 2910 to the power 6. So in order to put the powers, you can just put E in 6. Make sure that PSI is selected here. If it is already not, then click on the drop down menu beside it, and you can select PSI from the drop down list. Once you have entered the Young's modulus, put in the value of Poisson's ratio, which is 0.3. So now you can see that those yellow things has gone, which means that the required data for it to model an isotropic elastic behavior, you have already provided it to it. So that's why, sorry. So now you are good to go with a linear isotropic material. So everybody is on board up till this point. Everybody has done that. Or is there anybody who hasn't? All right, cool. So once you have done that, since we won't be using structural steel, so you can see that there are radio boxes beside, or the check boxes beside these materials, and at the top it shows suppression. So since we don't need a structural steel, let's suppress it. So if I click on this, it will go away. So this is the method of adding a material of your own choice, right? But there is a huge library of material or the commonly used engineering materials and their behaviors built into Workbench. So if you want to, or if you don't have specific values for these materials, you can use engineering data source and get the material behavior from that as well. So there are different kind of materials. I'm so sorry for my daughter. She's my daughter. All right. So, all right, where were we? Yeah. So I was saying that there are a lot of built-in material behaviors there as well. So you can use these materials as well. I will let you know, and we will use some of these material behaviors in the next tutorial as well. So you will be getting yourself acquainted with them, or how to use this data as well. So you can see that your material has gone somewhere, so don't worry. If you just click engineering data again, it will appear back. Once you have entered this material, just close this session, and you can see that the engineering data has a tick beside it. So it is in a way telling you that where we are right now and what we need to do next. If there is a tick beside it, it means that that portion has been taken care of. So you need to go and do the next part here and start creating your geometry. So it's already been 50 minutes. Let's have a short break. I think a 5-minute break will do, because we still have to do a lot of things. So let's take a 5-minute break, and let's meet back at, let's call it a 7-minute break. Let's meet back at around 12:30. Right, I hope everyone is back. Let me share my screen. All right. I assume that you are seeing my workbench screen, and I have unmuted myself as well. Yes, I have. All right. But the chat window is again gone. Participant window is gone again. Let me open them. All right. So we have created a new material, name it Agenium, and we have put in the isotropic elasticity properties for that. So that was the next step. Once we are done with that, next part is going to be creating the geometry of our problem. So let's go through it quickly. What we'll be doing in this part, we need to start the geometry environment here, which will open the design modeler. For those of you who have ANSYS installed on their own personal computers, there you may have two different options. One is something called space claim, and the other environment is called design modeler. So if you, is there anyone who is using ANSYS on their own personal computers? All right, Hamza, I'll show you how to start the design modeler environment rather than the space claim modeler, okay? So stay with me at that point. Then again, I'll emphasize on maximizing the window so that you see all the options once, and again, update the units once again. We need to create a geometry, a 2D geometry of 10-inch by 5-inch plate with a 0.5-inch diameter hole in the center of it. So let's quickly go to the next step. All right, so those of you who are using ANSYS on their personal computers, right click on this. You will see there are two different options. For us who are on HPRC, we only have one option called Neo Geometry. Sorry. But for those of you who are using it from personal computer, you must have two options there. One is Neo Geometry using design modeler. The other one should be Neo Geometry using space claim or something, I guess. So make sure that you right click on that and click on Neo Geometry using design modeler. All right, once I click on that, you can see that it is in the status bar, it is showing you that it is starting the design modeler. So that's why I was saying that the status bar should be seen so that you have an idea of what Workbench is doing at a certain point in time. Again, some of the portion is hidden here. So make sure that you maximize this window so that you see everything. Now you can see that what are the units used here and like what it is doing right now. So again, as I said, let's update the units first. Click on the units and make sure that they are in inches. All right. So once that has been taken care of, this is again the environment for the design modeler. This is where you will be creating your geometry. Some of the things, again, we have a toolbar at the top, kind of ribbon bar and toolbar mix kind of thing here. We have now a tree outline instead of the toolbox. And you can see that there are two different tabs here for the tree outline. One is the sketching tab and the other is the modeling tab. So you can differentiate between the two as something like in the sketching part, you will be creating the drawings for creating our 3D or 2D models, right? whenever we'll be creating any kind of geometry, the basic step or the first step is always going to create its sketch or a 2D drawing from which which defines the basic parameters of your geometry. So if we quickly go back, my geometry composed of a rectangle, and in that rectangle there is a circle in the middle. All right, the dimensions of the rectangle are 10 inches by 5 inches, and the diameter of the circle is 0.2. And for it to be in the center of the circle should be 5 inches from this or this corner, and 2.5 inches from the bottom or from the top, to make sure that your circle is at the center. So these are some of the things which we need to define in our geometry. So right now there is no sketch present here. So in order to create a new sketch, you need to click here on the new sketch button. So make sure that you find it here in the second row here, and it looks like or two triangles, rectangles with a small rectangle in the middle. So just click on that and it will add a new sketch under XY plane. So the default sketch is always going to be under XY plane, but if you don't want it to be under XY plane, so you can click on the plane where you want to create the sketch, click on that and then add a new sketch, and it will add the sketch on that particular plane. So right now XY plane is just fine for me. So let's go ahead and create the sketch. So I click on the sketch, and right now it is in the modeling environment, but since I need to work on my sketch, I need to go into the sketching environment by clicking on this particular tab here called sketching. So once I click on that, you can see that all these sketching options are shown here, and your environment has changed into this kind of crosshair. So since we'll be drawing everything on our XY plane, let's make our view perpendicular to that plane. In order to do that, you can simply click on this triad at the corner on the bottom right corner. And if you click on Z, it means that it will make your view perpendicular to the XY plane or along the Z axis. Now, once we are on this particular plane, as I said that our geometry, so let's familiarize ourselves with the sketching environment here. So we have a drawing options where we can draw a line, a tangent line, polyline, polygon, rectangle, circle, and curves and arcs like that. And if you click on this small arrow on the corner, there are some more options. So if you cannot find the option you are looking for, you can drag this thing by using these arrows on the corner. Once you have drawn something, if you want to modify it, then there is this modify tab, and all the modification options are listed under this modify tab. Then dimensions is a very important part of any drawing. So if you want to dimension your drawing or sketch, you need to create use the tools under the dimensions. In certain cases, you need to establish some kind of constraints for different things. So constraints can be established using the things or the options which are under the constraint tab, and some other settings and stuff. So let's go back. Sorry. Since our geometry is not that complex, we don't need a lot of things. Let's start with the basics. So the first thing which I mentioned that we need to have is a rectangle. You can create a rectangle using line tool. You can create 4 lines perpendicular to each other to create a rectangle, or the faster way is to use a rectangle tool here. There are 2 rectangle tools. One is this one using 2 points, and there is another one which is using 3 points. So if your rectangle is not not along your horizontal and the vertical axis, then you need to use the rectangle by 3 points. Since our case is along the vertical and the horizontal direction, we can directly use this rectangle tool. So just by looking at the icon, I can see that how we will be creating this rectangle. So you can see that there are two red dots at the corners. So this signifies that you need to first click where you want to start your rectangle, and you need to click again where you want your rectangle to be finished. So I have selected this option. I will put my roughly towards this black dot or the center. I click once and drag it. Some of you may see this rectangle outline while creating it. Some of you may not. Don't worry. Once you have clicked on the first one, if the dimensions are roughly equal to what you want them to be, click again and it will create the rectangle. Once you have done that, the next step is going to be creating a circle in the middle, or roughly in the middle. You can see that we don't know what the dimensions of the rectangle are, but we need to make sure that the dimensions are right, but we are not bothering about that. We are just creating all the features of the sketch which we need, and we'll dimension them later. So once that has been taken care of, let's create a circle in the middle. So for that, I have selected the circle tool. Again, if you just look at the icon of the circle, you can see that there are two small red squares, one at the center and one at the periphery of the circle. So it means that, again, in order to create the circle, you need to click twice. The first click is going to show where you want to have the center of the circle, and the second click is going to show where the periphery of your circle is going to be. So once you have done that, selected this option, just go and roughly in the center, click once to establish the center of the circle, and keep moving out to create the circle. So you can see that it's not to the scale, it is not at the center, but I'm not bothered about that just yet. I'll dimension it to be, I'll give the dimensions to it to make it perfect. Once that's taken care of, let's go to the dimensions tab. So we need to establish some dimensions here first. We know the diameter of the circle, so there are different options here, and you can find this option of diameter here. Just click on that and click on the circle and click somewhere to put that dimension. So each dimension will be named like D1, H1, V1 and stuff like that, and their values will be shown here under the sketching and modeling toolboxes. Okay, so these are the properties of your sketch. So you can keep on changing the values of the dimensions you have assigned here in this particular area. So since the diameter of your circle was 0.5, so just click here and enter the value 0.5 and click enter. And you can see that the dimension of the circle will be updated. Once you have dimensioned the circle, let's start giving the dimensions of the sides of the rectangle and the location of the circle. So if for doing that, I'll use the horizontal tool. So horizontal tool is used for giving the horizontal distance between 2 points. So since we will be defining the horizontal distance between these two lines, let's click for once on this line and then click again on the other line and place this this dimension anywhere outside the rectangle. So where you are placing this doesn't matter, because these dimensions are not part of your sketch. The sketch is this blue lines. So the green lines are not going to be your geometry or the part of the sketch. So this distance is supposed to be 10 inches. So let's update that. Then I need to establish the vertical distance between the top and the bottom. So again, I selected the vertical option. I clicked once on the top and then again on the bottom and place this dimension outside the rectangle somewhere. This is supposed to be 5 inches. Then comes positioning the center of the circle. Now you need to do exactly the same things, by using the horizontal and vertical, excuse me, by using the horizontal and vertical dimensionings. So the vertical location of the center of the circle and the bottom line, I'm going to put here. This is supposed to be 2.5. I'll update it to 2.5. Then again, a horizontal dimension from the center of the circle to this corner. And this is supposed to be, where it is placed, H5. Yeah. So this is supposed to be 5. So it will update it. So there were two features of our sketch or of our geometry. There was a rectangle and there was a circle in the middle of the rectangle. Dimension of the rectangles were 10 inches by 5 inches. Diameter of the circle was 0.5 inches, and the circle was placed in the middle of the plate. So these H5 and V4 made sure that the circle is exactly at the center. Once you are done creating your sketch, you can go back to the modeling environment by clicking on this tab here. Then what I need to do, I need to create a solid body out of the sketch which we have just created. And for doing that, what I'll do, I'll just click on the sketch here to make sure that this is the sketch on which the next operation will be applied. Then I'll go to concept. In the toolbar, click on the concept, and there are different options here. What I want to do, I want to create a surface from the sketches which I have just created, right? So right now, the sketch on its own is nothing but a drawing. All right, it is not a physical feature. It doesn't have any thickness. It doesn't have any weightage or any material added to it, right? So in order to make it filled with the material which we have assigned to it, what we need to do, we need to use an option called surfaces from sketch. I've mentioned that our analysis is going to be a 2D analysis. So the highest order of dimension which we go in the 2D case is an area or a plane or a surface. So that's why this is the only thing which is highlighted from here. So click on the surfaces from sketch. Once you have done that, you can see that in your tree outline, there is a new entry called surface SK1. It may have some other name in your case, but the important thing is that this will be added here. You can see that there's a small thunderbolt sign beside it. You will come across the thunderbolt sign a lot in the ANSYS. If there is a thunderbolt sign beside something, it means that you need to take some action here. If there is a tick mark, it means that you don't need to take any action there. But for every thunderbolt sign, it means that there is something you need to do. So what it needs to do, we need to generate this particular thing. We have defined it, but it is not executed or generated yet. So in order to generate it, just highlight it and go and click on generate. All right, so it says that base object is not selected. Is there anyone else who has this issue? All right. All right. So let's try it again. I'm gonna highlight a sketch one. Then I'll go to concept and click surfaces from sketch. All right. This is the thing which I forgot. Once you click on the concept surfaces from sketch, you can see that the properties window under the sketching and modeling has changed, and it shows detail of sketch surface SK2. So it is expecting you to confirm that this is the sketch you need to assign for creating the surfaces. So what you need to do, click on apply first, and then click on generate, and it will generate now. So once again, let me delete it and go over those steps again. So I'll select a sketch one, I'll go to concept, click on surfaces from sketch, and under the tree outline, there are the properties. And it is asking you to confirm that this is the sketch which you want to use to create the surface. So click on apply to confirm this selection, and then go and click on generate to generate this material. So now you can see that the material which it has added is shown in light gray color, which means that the actual surface of the material has been added in this particular region. Once that's taken care of, it's a very good point in time to start saving the work. So you can save the work here, or you can simply close. Make sure you are closing the design modeler and not the workbench. Make sure that you have DM, a small DM written here, and close only this window, not the workbench window. Okay. Now you can see that beside the DM geometry, there's a small tick mark sign which shows that the geometry has been taken care of. So let's go here and quickly save our project. So make sure that you are already here in the Scratch user and whatever net ID you are using. So let's name it FEA 1, or let's give a meaningful name, plate hole. It's a good practice to try not to use a combination of the capital and the small letters while you are working on a Unix system, if you are on HPRC. And one more thing which is very good practice is not to use any special characters or spaces while you are on a Unix system, because it will create some troubles. Not only for ANSYS, but anywhere or any other software you will be using on the Unix system. So try not to have spaces in between the names, and try not to use a combination of capital and small letters. Click on save, and now your project has already been saved. Just to check that it has been saved, go back to the file explorer, and you should be able to see the files in your Scratch directory. If it is not, just refresh it and it should appear. It should appear there. All right, let's go back. Now let's see what's the next step. So we are done with the geometry part. Let's go back to the meshing. So meshing, in order to do that, we need to double click on the model in the structural, static structural thing. We need to maximize the window again to see all the options which are there, the whole environment of the modeling environment. Again, we need to update the units first. Then the things which we need to assign is, we need to follow my instructions to discretize, a thing called discretization. I'll explain it while I go through it in a little while. We'll discretize the geometry, whatever geometry we have, into elements of sizes of 0.1 inches. And we will refine these elements up till 3 times around the hole. How to do that and what it is, let's go through it now. So in order to do that, first of all, again, you can see that there is this recycle kind of sign beside model. It means that it requires something or some data at this stage to proceed forward. So it is like intuitive to just keep on following from the top to bottom. So let's double click on model. You can see that it is saying starting mechanical. So don't worry, just be patient till this status change. All right. So there's some disclaimers saying that you may have some cosmetics error. I already have one in the corner top, so don't worry about that. Just click on OK. Usage tips, you may want to have a look at them while you are doing it on your own, but since you already have someone to take you through all the things, so you don't need that either. Close that one as well. Again, make sure to maximize it. Once it is maximized, you can see that Workbench has already imported whatever geometry we have created earlier. Just give me a second. All right, so the geometry has already been imported into this environment. You are looking at it from a perspective view. Let's click on again on this triad on the Z here to have a look at the 2D two-dimensional view of it, or a planar view of it. So again, as I told you, that you need to make sure that the units are consistent. First, make sure that you have changed the units. In this environment, you can change the units by just looking at this status bar at the bottom. Right now, it is US customary. If you just click on it, just change it to, all right, so it's cool. US customary is inch, pound, mass, and pound force. So this one is fine for me. So leave it at it. All right, so I told you that look for a small Thunderbolt sign beside different things under the project tree, under the tree outline. We can see that there are certain question marks here. I'll come back to it in just a little while, but for now I'm focusing on the meshing part. You can see that there is a small Thunderbolt sign, which means that this is something which you need, which needs your attention. So just click on the mesh, and you can see that the ribbon bar options has changed to be consistent with the meshing environment. If it has not, just click on the mesh at the top. Just click on the mesh at the top, and you will start to see all the options related to the meshing. All right. So if you recall, I told you that we need to mesh our geometry into elements of size of 0.1 inches. So let's do that thing first. So there are different methods. So what meshing itself usually has. So if you recall, if you have taken some solid mechanics course during your undergrad or your early years of undergrad, you may recall that we used to do some kind of analysis in which we have a stepped bar. Okay, so we have a bar which has different cross sections for different lengths. So what we used to do in that case, we used to divide those bars into different sections, and the sections used to have constant cross sections along their lengths. So that is one of the way of looking at discretization. So discretization, what usually does, so right now this whole geometry is a continuous body. The problem was that no analytical solution exists or analytical relation exists to solve this particular nonlinearity where we have a hole in the middle. Okay, and in order to do that, in order to solve this kind of problem, we are using FEA. So what FEA is going to do, as the name suggests, it's called finite element. So what it does, it divides or discretizes this whole geometry into small elements, and each finite number of elements. The number of elements can be very high, but it will have a finite number. Hence the name finite element. So what I'm going to do, I'm going to divide this whole geometry into small elements, and we know the physics of each of those elements. That's why we will be able to do the analysis on it. So what I mean by the physics and everything, I'll just come to it in just a little while. Right now, what the thing is to understand that we need to divide this whole thing into finite number of small elements whose physics we already know. The second thing is, whenever you are discretizing something, the smaller the size of the elements, the better the solution is. I repeat, the more the number of elements you have and the smaller the size of the element, the better the accuracy of the solution is. But the problem is that in most of the cases, you don't have very high computing power. And in most of the cases, it is not worthwhile to go beyond a certain limit of elements, because the accuracy of the result is not changing or improving that much. So we need to make a trade-off between the accuracy and the amount of time it requires to do the analysis. So 0.1 inch size elements is a very medium sized mesh. It is not very fine. It is not very coarse either. The results are gonna be pretty accurate as well. So let's go ahead and just start doing this meshing thing. So the options you have right now, if you go from the corner, it has a solve option, it has update, generate, then there are previews, there are controls and stuff like that. So if I just click on generate as is, so the status bar changed and it just roughly discretized the whole region into small elements. So each of these blocks are called elements. These small blocks are made out of corner points, which are called nodes. You may not be able to see here, but in different softwares, they make sure that you see the nodes as well, because there are certain solutions which are only available at the nodes. Let's not go into the details right now. Let's focus only on the elements. So you can see that the elements are pretty big here, and we have very sharp jumps in going from here to here. And if I zoom in, for zooming in, you just have to click here anywhere and scroll your mouse. So if you scroll it, in my case, if I'm scrolling it up, it is zooming in, and if I scroll it down, it is zooming out. So if you zoom in, you can see that the surface of the circle is not very good. So it is not a circle, rather it is a polyhedra. I don't know how many sides it has. So, sorry, a polygon, not a polyhedra, polygon. So it is a polygon. So one of the inaccuracy we are already introducing in our system by selecting a very coarse mesh is converting our circle into a polygon, which is definitely not desirable. Okay. Another reason of refining the geometry or refining the mesh in a certain location is to be able to get the results where the most of the activity is happening. So maybe there is not a huge shift or like jumps in the stresses, and this region is going to be far away from the hole, but in the vicinity of the hole, there will be a lot of activity and the value of the stresses may be changing very rapidly. So if you want to be able to resolve or to be able to get the values in the vicinity with a very high accuracy, you may want to mesh a very refined mesh around the area of interest. So let's call it area of interest, the areas where we are interested in getting the results. All right. So this was the coarsest mesh. Definitely, if you just click on the sizing, I don't know whether it is showing. Yeah. So you can see that the default element size right now is 0.88 inches, which is quite coarse. You can do the analysis. It will give you the results, but as I told you that the results may not be that accurate. Okay. So the reason we are going to be doing the refinement is to improve on the accuracy of the results. All right. In order to increase or decrease the size of the elements in this thing, let's click on sizing. Once you click on the sizing, there are, again, as I told you, that if there is a yellow area, it means that these are the inputs you have to provide. Okay. So the first yellow area is asking us to give the geometry where I want to apply this sizing. Okay. So we will be sizing this geometry. So what I need to do, so if you look at the top under the ribbon bar, there is another bar. I don't know what it is called, but there is this small arrow with a small point here, then an arrow with an edge, then arrow with the face, and then arrow with the whole volume. Okay. So right now, since I'm interested in selecting a surface, if it is already selected, I need to click on this icon, which will let me select a surface. Okay. So if I just click on that and click on the surface, it will select this thing. So whatever is selected is going to turn green. All right. If I click somewhere else, it will unselect it. If you want to select multiple quantities, you need to keep on pressing Control key in the Windows. I don't know what control key. Do you have control key in the Mac as well? I don't know. I guess you have. So you need to keep on pressing the Control key on either Mac or Windows, and you can select multiple features as well. If I want to size one of the edges, okay, so what I'm going to do, I'm going to click on this thing. And now if I try and click here, it is not going to select the face. But if I go to one of the edges, I may be able to select it. So the selected edge is going to turn green. So if I want to do this or this edge or this edge or this edge, I need to press the Control key. While pressing the Control key, I'll do the multiple selections. If you want to unselect it, just click on it once more to unselect this thing. But since I want to have a size of this whole face, so I just select this face thing, click on it, the whole face will turn green. Come to this geometry thing. If you click on it, the option for it's going to ask you whether to apply to this geometry or not. Since I want to apply on this geometry, I'm going to click apply. The next thing it is asking me is the element size. So let's change the element size to 0.1 inches. Okay, as soon as you do that, you'll see that again we have a Thunderbolt sign beside it. This shows that it needs your attention, or like you need to click on generate here to update this change. So let's click on generate. It is going to take some time this time around. Now you can see you have a pretty uniform mesh. You have some disturbances here and there, but since they are far away from our area of interest, we don't bother about that. Now the distribution of the size of the elements are pretty constant all about. We want that. We don't want sudden changes in the sizes. This is like a good practice. And we, in most of the analysis, we want them to be have like there's a thing called aspect ratios. So what aspect ratio is, if I click on it and zoom in, you can see that each of these elements are in a very good square shape. You can have elements in trapezoidal shapes or rectangular shapes, but we definitely don't want our elements to be very long and thin. So that is something called aspect ratio. The aspect ratio is basically the ratio between the length and the width. So if we have a very high aspect ratio or a very small aspect ratio, we want the aspect ratio to be roughly equal to 1. Okay. So try not to have a very high or very small aspect ratios. Keep them roughly at around 1, and especially not in the region where most of your things are going on. Now let's zoom in again to the circle or the hole. Now you can see that the number of sides of our hole has increased. Before, the polygon was of roughly 10 or 12 sides. Now it has more than that. But again, it is not very circular either still. Okay, so that's why we are going to be doing our next part, which I mentioned you during the slides, that we need to refine it up to 3 times around the hole. So whatever the mesh we have created in this region, this is fine for these regions, but it is not fine for showing this particular area around the hole. So for doing that, I'm gonna click or select something called refinement. Just select this option, refinement. Now again, it is asking you for the geometry to refine. This time around, there is no face here to select, but since there is this edge around which we want to refine it, I cannot select this edge, because if I click here, it is going to select the whole face, and I don't want to select the whole face. I don't want to refine the whole thing, rather the mesh only around this edge. So I'm going to select this edge selection tool and just click on this circular edge. Once you have done that, click on apply to confirm that this is the geometry you want to refine. And there is a thing called refinement. So this is the ratio of refinement. So if it is 1, it means that it's not going to refine anything. I doubt you can go in any value less than 1. So you cannot make it any coarser than that. But in order to refine it, what you're going to do, you can just click on this buttons to increase or decrease the level of refinement. So I guess the maximum you can go is 3 in this case. So once you have gone up till 3, come back to the tree view. You can see that there is a thunderbolt sign beside the mesh again. It means that it needs your attention. Just click on the generate again. It's going to take some time to update the mesh. And voila, you can see that your circle is more like a circle now. Okay, it's no more a polygon. And as I told you that most of the variation is going to be happening here, you will be able to capture that variation because you have more elements around your circle or the hole. So this is all about the meshing part. Now let's go back to the slides. We are done with the meshing. Let's go and see what the physics steps is all about. So for the physics step, we need to continue the mechanical interface. The steps which we need to carry out, or the tasks in this step, is to assign the material properties created during the startup to the mesh geometry. We need to select the behavior of the geometry as a plane stress and assign a thickness of 0.2 inches to the geometry, because if you recall, the thickness of this plate was 0.2 inches. Okay. So we need to assign a thickness of it. Then we need to apply some kind of boundary conditions because this is a closed form solution. It will we need to give some kind of boundary condition for it to be able to solve for the stresses and the displacement within the geometry. So the boundary conditions which we require are frictionless support, which are fixed displacement normal to the edge plane and no traction along the edge of the plane. What it is, how it is applied, I'm going to explain it in just a little while. So we need to apply the frictionless support on the left and the bottom edges, and we need to apply a pressure boundary condition on the right edge. So let's do the physics step. So the physics step, you don't need to go into any other environment in order to do that. But before doing that, it's good practice to let's save it first. So since we are done with the meshing part, let's first save the project and the progress of the project. Once it is done, you can click here somewhere to maximize it again. All right. So what we need to do now, so we have discretized our geometry into small portions, but the software still doesn't know what is going to be the behavior of this material. Okay, so, or the behavior of this geometry. So in order to completely explain the behavior of this geometry, I need a couple of things. So the first thing which I'm going to do is to establish that this is a two-dimensional problem. So if you recall, when I was starting the meshing part, I was telling you that it is a good practice to try to make a trade-off between the accuracy and the accuracy of the result and the time of computation required. And again, so keeping that thing in mind and keeping this thing or like recalling something from our elementary solid mechanics things, that there are certain shapes and sizes of the specimen or the bodies in which we can take some kind of approximations. So some of those approximations are plane stress and plane strain, and one is axisymmetry. Although everything which exists in the real world are three-dimensional in nature, and that's the only reason we can hold on to something, but we can assume some of these things to be two-dimensional by taking some kind of approximations. These approximations help us in this during the solid mechanics. It used to decrease the amount of calculations we need to do without losing a lot of accuracy. And in this case, when we will be doing FEA, it will result in pacing up the time required to solve something, some analysis, or to pacing up the analysis. So although this plate is three-dimensional in nature, but I can safely assume it to be two-dimensional, reason being that the thickness direction is very small as compared to the other two dimensions. So we have a length and the breadth of 5 inches and the thickness of only 0.2 inches. So for this case, we can safely assume it to be a case of plane stress. So starting from the top, first of all, I will update it to be two-dimensional. It is a flexible body. It can change its shape, so keep it flexible. In the 2D behavior, if you click on it, we have different drop-down menu. We can have a plane stress, we can have axisymmetric, we have plane strain, and we have general axisymmetric. So since this is a problem of a plane stress case, so let's select plane stress. When you select the plane stress case, the thickness of the body is of interest and important. So just click here and enter the value of thickness of 0.2 inches. Okay. There is a question here. It says that, can you show the face sizing detail page? Okay. You're talking about this one? Joshua. In the tree. All right. This is you're talking about? All right. So I have selected the geometry and selected this face and updated the element size to 0.1 inches. These were the two things which I've changed here. All right. So where were we? Surface body. Yeah. So I have assigned a two-dimensional behavior to this particular geometry. I have assigned the behavior, 2D behavior of plane stress case because it is a thin plate. Thickness of the plate is assigned as 0.2 inches. The next yellow area which needs my attention is the material assignment. So the one of the most important thing is for the mechanical environment to know is what is going to be the behavior of the material. So since we are doing mechanical analysis, it is going to be interested in the mechanical properties of the material, depending on the regime you want to model it. So if you recall, we have already established our material in the engineering data thing at the very beginning. So if I just click here, there is a small arrow. If you click on that, the material which we created should be here. And if it is not here, if there are some certain cases where it does not automatically appear here, then what you can do, you can maximize here. It will have to be here somewhere. And even if it is not, you can see that there is a thing called new material here. You can click on the new material and create the material again and assign that material properties to this geometry. So since we have already created the material aginium, I have selected that. Now you can see that the question marks had turned into tick marks, which means that we have already established whatever tasks are there for our attention, or like which need our attention. So I don't know why it is showing a sign here. Let me generate it again just to see what's wrong here. All right, cool. Now you can see that this bold sign has come to the solution and solution information. So before going into this part, there is still a question mark here in the structural part. So we need to do some things here. So as you recall that I wanted to apply some boundary conditions here. So let's apply those boundary conditions so that we can run the solution. So for doing that, click on a static structural. And you can see in the ribbon bar has updated to something which has some boundary conditions involved here. Okay, so on this side, these are some kind of boundary condition which are load boundary condition or force boundary condition type, where you can apply some kind of force, moments, pressure, and stuff like that. And if you click on this small arrow sign, there are other options which you can select. Okay, and on this side, these are structural. We call it displacement type boundary conditions. So some of them are directly here, like support, fixed, frictionless, and displacement. And if you click on this drop down menu, you have some more type of boundary conditions. So if you recall, we wanted to apply a frictionless support on the left and the bottom edges. So let's do that first. So the frictionless support is here. So this is the frictionless support thing. Just click on it. So it is asking you for the geometry where you want to apply this boundary condition. So if it is not already selected, click on the edge selection tool here at the top. While pressing the control key, select the left edge and the bottom edge. Once both of them turn green, click on apply. So you can see that there is a small arrow, filled blue arrow, which is showing that where the frictionless support has been applied. Okay, so what does the frictionless support do? I have given an explanation here that frictionless support has fixed displacement normal to the edge or the plane where it has been applied, and there is no traction along the edge or the plane. So what does that mean? It means that this frictionless support will not let this edge, if we are talking about the bottom edge, to move in the vertical direction. It will resist any kind of motion in the vertical direction. It will allow motion in the horizontal direction, but it will not allow any kind of vertical direction. And there will be no forces along the horizontal direction. So hence the name frictionless, that it will not create any kind of traction along the horizontal direction, but in the vertical direction there will be some kind of reaction force, equal and opposite to whatever is applied here. Similarly, if we are talking about this left edge, it will not allow this edge to move in the horizontal direction. It will be free to move in the vertical direction. There will be no traction in the vertical direction, but there can be some reaction forces along the horizontal direction. So this is called a frictionless support. You can create a fixed support as well. So what does the fixed support does? Fixed support will not let it to move either in the horizontal or the vertical direction. So it constrains the edge or the face to move in any direction. Okay, so that is a fixed support. Frictionless is as what I have explained it to you. Then displacement is something, if you know that how much displacement is going to be on this face, you can apply displacement on this face to pull it in the horizontal or the vertical direction. Then on this side, if you know what is the amount of concentrated force at a particular point, you can apply the force. If you know the amount of moment at a particular location, you can apply that moment on any body. Pressure is the load which we already know is being applied on the right hand side. So let's apply that boundary condition, which is called pressure. So again, it is asking me at where I want to apply that pressure. So I want to click it here. So select it on the right edge and click apply. So the pressure will always be applied, as you all know, that pressure is the force or the force per unit area perpendicular to the edge or the face where you have applied it. So it will always be perpendicular to it. So the magnitude, if you apply the positive magnitude, it will always, let's apply it first. So it is 1 exponent 6. So wait a second. So pressure will always be applied inwards. Okay, so by default, whenever you apply a pressure to a body, it will be applied inwards. Okay, so since the distributed load in our case, if you go back here, it is directed outwards. So what you need to do, you need to apply, enter a negative sign at the very beginning for it to be applied outward. Okay. So once that has been taken care of, we have established our physics part. So in the physics part, what we have done, we have defined the behavior of each of the elements, and we have defined the boundary condition in this case. Once that is done, let's go to the next step where we will be doing the solution and the results part. So we will continue in the mechanical interface. We are looking for the results in the form of deformation. We are interested in the deformation of these elements. We are interested in the radial, tangential, and the normal components and the shear component of these stresses. And the normal stress is going to be along the x-axis. We will be solving the results, and then we'll look at the solutions for the deformation and stress distribution in the plates, in the plate. So let's go back. Again, it is a good point to save it again, once again. So go back to the workbench and save the thing. Now you can see that the model part has a tick mark beside it. It means that all the things required for these operations has already been taken care of. Now these are the only things which are still left. So let's go back to the mechanical environment. So in this thing, you need to tell the system or the ANSYS what results you are interested in. So as I mentioned that you are interested in the deformation. So again, when you click on the solution here, the ribbon bar will change and all the options available for the solution environment are listed here in the ribbon bar. So first of all, let's include the total deformation. So what it will do if you run the solution now, it will give you the solution in the form of total deformation. Okay. Then there is a normal stress. So let's go here and click on the normal. So now it will add a normal stress for the sanity check. Since we have a lot of normal stress components, keep on renaming the outputs here. So I will just right click on it and click rename and rename it to normal stress dash XX to show that this is the normal stress in the X direction. Okay. You don't have to update anything here because by default, the orientation is selected at X axis. Okay. We are interested in the radial and tangential stresses and a shear stress in the R theta direction. So the coordinate system here is an XY coordinate. Okay. And the radial and the tangential stresses are in a cylindrical coordinate system. So what we need to establish here is to get a radial coordinate or a cylindrical coordinate system first. So for doing that, go to this option here, which is called coordinate system. Okay, right click on it and there's an option called insert, and there's only one option to insert a coordinate system. So just click on the coordinate system. It is asking you what kind of coordinate system you want to add. So we are interested in a cylindrical coordinate system. So select it from the drop down menu. Select this, make it cylindrical. It is asking you where to position this origin. So click on this and select this edge of the circle. So if you select it, what it will do, it will position the center of this coordinate system in the middle of the hole. So click on apply. So you can see that it has shifted here. Although it is a cylindrical coordinate system, but its components are called X and Y for some weird reason. It is still not called R and theta coordinates, so don't worry about it. But just establish it that the value of R or the R direction is called X in this thing, and the tangential direction, the theta direction, is labeled as Y. Okay. Once you have established this coordinate system, go back to the solution environment, and now add one more normal stress. So click on the stress, click on the normal stress. Now it is asking you for the scoping method and different things. If you look here under the definition, there is a field called coordinate system. Click on that field. Wait a second. Let's first rename this coordinate system. So let's call it cylindrical coordinate system. Okay, just for the identification purposes. Coming back to the normal stress, if you click on the coordinate system again, now there are option of selecting global coordinate or the cylindrical coordinate system. So click on the cylindrical coordinate system. Now we are interested in the R component of normal stress. So R, as I told you, is labeled as X here. So leave it as is and rename it as R. Okay. Similarly, establish one more normal stress, same procedure, selecting cylindrical coordinate, but this time around, don't leave it at x-axis, rather make it y-axis. Okay. And again, rename it to theta. Okay. Now the last one is a shear component. So click on a stress and add a shear stress. This one again is on the cylindrical coordinate system, and there is only one option of XY plane. So leave it as it is XY and rename it to R theta. So all the solution or the results we are interested in are already established here. So the only thing left to do is to solve this problem. So for doing that, just click on the solve here. If you click on the solve, the solution will start. Is everybody along with me? Is anybody stuck somewhere? All right, I assume that everybody's on board and nobody has an issue. All right, cool. Wait a second, there has been some problems. All right, so you can see that there are checks on all of the components here. This signifies that the solution, that everything which required your attention has already been taken care of. Beside each of these fields, you have tick marks as well, which shows that the solution has already been done. Again, this is a good point to save your results before analyzing them. So just minimize it And you can see there are tick marks all over this place, which means that all the steps has already been taken care of. So just click on save, and your progress has been now saved. Now let's go back and see what to look for in the solutions. So there are solutions of deformation and stresses, which we have already seen. So there are, as you recall, that we were interested in, let me drag this slide down so that we have quick comparison between the two. Okay. Yeah. So we were interested in the displacement. We were interested in the radial stress, tangential stress, shear stress, and the normal stresses. So all of these things are plotted here. You can, yeah, this type of representation of the results is called contours or contour plot. So contour plot basically tells you the distribution of a certain quantity within a body. So there are two things which we need to look into. One thing is that we are looking at the deformed body. So this outline, if you click here, so there are different options. One is no wireframe. So this is the deformed shape of our plate with the hole. If you click it again, and there is another option called show undeformed wireframe. So now it is plotting both the undeformed shape as a wireframe and the deformed shape as the solid contour. You can only see the contour, and if you want, you can see individual elements as well. Okay, so these are the options. I'm right now interested in this one because it is giving me a brief comparison between the two. Another thing which is very important in any contour plot is the legends. So you have to have this thing plotted whenever you are reporting any contour results. So there are two things which should be mentioned here. One thing is what you are plotting here. So that can be read here. We are plotting the shear stress, which is the R theta shear stress. Okay. The other thing which we are interested in is the magnitudes. So what it has done, it has binning different ranges of the values in different colored bins. So for example, this red color bin tells me that the value of shear stress R theta is between 5.2 exponent 5 to 6.7 exponent 5. So wherever we see this red region, the value of shear stress is going to be between these terms, which is 6.7 and 5.2 exponent 5. And if something is in cyan color, it will be in between -2 and -3 10 to the power 5 value, wherever this color is appearing. Another very important thing to include with your legend is the units. So in order for your results to be meaningful, you have to mention what units these values are. Okay. So let's start from the top. So this is the total deformation contour. You can see that the blue color is where we have a deformation within the range of 0 and 0.03 inches. And the red region is the region where we have deformation between this values. So the maximum amount of deformation which we are getting out of this thing is 0.35 inches. If you quickly go back to the analytical results of the plate without a hole, we were assuming that this deformation, this displacement at this end should be 0.34 inches. But keep in mind that this was the calculation for without a hole. So this is the case where it is a solid body. So for a solid body, it will, excuse me, for a solid body, it will deform very less. Just give me a second. Let me grab water.
So while we're waiting and we're getting close to the end, if you could please fill out this short course survey with a little bit of feedback. It's anonymous and we value your feedback.
I guess the polling is underway. Lisa, let me know once it is done.
You can go ahead.
All right, thank you. All right, so we were discussing that the displacement without the hole was supposed to be 0.34 inches, but since we have introduced some kind of weakness in our structure, it was bound to have more deformation than this case where we don't have a hole. And that is reflected here when we are getting a value of deformation at this free end of somewhere around 0.35, which is definitely more than 0.34. So I assume that you appreciate the difference between a solid plate and the plate with a hole. So, and why there is a difference between this thing, between these two. Okay. Then the next result which we were interested in was the radial stress. So I passed through real fast when we were discussing this thing because at that point it was very confusing, but now it started to make sense. So the value of radial stresses and what values to expect are mentioned here. So again, keep in mind that these results are for the case where we have infinite plate with a hole in the middle. Okay, these results are for that, but we can get a good approximation from this analytical relation. So the analytical relation tells me that the value of radial stress at the boundary of this hole should be 0. Okay, and the value of radial stress far away from the hole, okay, which is if the value of R is very big then as compared to A, which means that we are very far away from the hole, the value is approximately equal to this thing. You can still see that it is a function of theta and sigma naught. Okay, you can do the hand calculation later because we are running short of time, so I'll just go through real fast about for this one. So let's go back to the results. I am now plotting the radial stresses. Just to avoid the confusion, let's remove this thing. Okay. So if you look at it, we can see, and another good tool to read the result is called probe. So if you click here on the probe and you drag, yeah. So if you click on the probe, select the probe option and click anywhere, it will show you the value of the result at that particular point. Okay, and the result definitely is going to be whatever you are plotting here. So the value of radial stress at this location is roughly 110 to the power 6, the value of stress which we applied here. So this is what we learn here. If you substitute the value of theta as 0 here, okay, because sorry, 180 degree here. So 2 times 180 is 360. So cos of 360 is going to be 1. 1 plus 1 is 2. So the value of radial stress roughly is going to be equal to whatever we have applied as sigma naught. So sigma naught is the applied stress. So we applied a stress of 110 to the power 6. So along this line, the value of very far away from the hole should be roughly equal to whatever we have applied, which is 110 to the power 6. And we are seeing that that value is appearing here. Again, there is a deviation from the exact value, which was 1. There are 2 reasons for that. One reason is that this is an approximate value here. The exact values can be calculated using this relationship. And the other thing is that this result is for an infinite plate, not for a finite plate. But even taking those assumptions, the values are well within the range of whatever we calculated using the analytical results. Another thing which, all right, so here at 90 degree, the value of stress is very, very small. So here it is of the orders of 10 to the power 5. Here it is of the order of 10 to the power 3, which is in comparison is very small. Okay. So if we apply, if we enter the value of theta is 90 degree here, so 2 times 90 is 180. and cos 180 is -1. So 1 minus 1, it will become 0. So for an infinite plate, where very far away from the hole, the value will be 0. So we are seeing not 0 because we don't have an infinite plate and we are not very far away from the hole. We are getting some finite value, but in comparison to these values, it is very small. Okay, so that is being proved as well. Another thing which was that the value of stress, if I zoom in, which stress is that? There was some confusion. R is equal to 0, A sigma is 0. Yeah, so if you select something at the very corner, at the very edge, you can see that the values is appearing as very small value. Although even if you go a bit farther away, there is a huge jump, but at the very edge of it, you are getting very small values. Again, you are not getting exactly zeros because we don't have an infinite plate, we have a finite plate. That's why there is a difference. But again, that difference is not like you still can make some comparisons even with those differences. That the comparison is that the value of stress is very small, very near the hole. This is what I was talking about, that most of the things are happening around the hole, and these values are only calculated at each element location. If I plot the element as well, so the value of stresses is supposed to be calculated only within this element. Okay, so if you want to have a better resolution around your area of interest, you need to improve the mesh around it so that it resolves the values near those regions better. Okay, so if I zoom out, same things can be extracted in your own time as far as the normal stress components in the theta direction and the normal stress in the x-axis direction are concerned. You can probe these values for different regions near the hole, farther away from the hole, and see what the results hold. So you should be able to get, so I have outlined all these expected results here, that the value, if we are talking about the sigma theta values at r is equal to a, it should be something equal to this, and very farther away from the a, it should be something equal to this. And the value of shear stresses near the hole and farther away from the hole are mentioned here. You can do all of these things in your own time and like play around with it and see, just verify whether the results we are getting are within the limits or not. One more thing was that the normal stress or the maximum amount of normal stress using this particular analytical solution or the empirical solution was telling us that it should be somewhere equal to 3 times whatever this load we have already applied. So let's see whether we are getting that or not. So now I'm plotting normal stress XX. So we can see that the maximum value of normal stress in the X direction is 3.01, which is a very good approximation of the empirical solution we already have for a case where we have an infinite plate with a hole. So this whole procedure is, or like FEA on itself, is a very good tool for solving the problems which cannot be very easily solved using analytical or hand calculations. And for the cases where we want to optimize some designs and stuff, so these are some of the applications where you use finite element analysis. Or in cases where you create something called digital twins, where you don't want to do all the experiments in the real world, rather you do some experiments in the real world, and using the data which you have extracted from them, you take it to the simulation tools and then do the rest of the experiments in the simulation environment. So all these applications are there for FEA. Quickly moving forward, so these are the solutions which you can compare in your own time. This was the verification part, which I've already done. Yeah, since we